Hi everyone. So today we're going to start wrapping up Module 2. This is a bit of a long module, but we're going to focus on sections 7.1 and 7.2. All right, so in Chapter 7, we're interested in chemical reactions and quantities, although for now we're just going to focus on chemical reactions. All right, so remember previously I talked about how pure iron can react with moisture and oxygen in the air to produce rust. So I kind of wrote out a simple equation here. Iron plus oxygen reacts to form rust. So this is an example of a chemical equation. Now, we're going to start using actual element symbols and compounds for our chemical reactions. And off to the right, you can see pure iron and rust. Now, first, let's review chemical changes. So a chemical change, remember, occurs when a substance is converted into one or more substances with different formulas and different properties. So similar to our iron and oxygen example. Now off to the left, we have another example of silver tarnishing. So if you've ever noticed your silverware getting a little gray or dark gray, that's tarnish, and that can either happen when silver reacts with oxygen or with sulfur. So there are different ways that we can determine if a chemical change has occurred. So for instance, a change in color, like with the tarnishing of silver or the formation of rust. But additionally, some reactions will produce bubbles or gas. We already talked about a change in color. Sometimes you'll notice that a solid is forming. So, for instance, if you mix certain liquids together, they can form a solid, and we'll talk about that type of reaction later. Or maybe heat is released or absorbed when two chemicals are mixed. So, for instance, if you mix two chemicals in a beaker, and you feel some heat coming off of the beaker, that's an indication that a reaction has occurred or that a chemical change has occurred. All right, so your textbook does have a table kind of summarizing these different types of evidence of a chemical change or a chemical reaction. So we talked about change in color, and rust was a really good example. Another example, if you see a gas forming. Now, in this particular reaction that's shown, calcium carbonate, which is found in antacids like Tums or Mylanta, that reacts with acid to produce a gas. And then we just talked about the formation of a solid, which we actually call a precipitate. So we'll talk more about these types of reactions later, but in the picture below you can see that there's a yellow solid forming in a clear liquid. So this happens when two liquids or chemicals, potassium iodide and lead nitrate, are mixed together. All right, and then the last example, if you feel heat coming off of a reaction or off of a beaker, for instance, then you know that a reaction has occurred. Or if you feel that the beaker is cold, that's another indication that a reaction is occurring. Okay, so now let's actually write some chemical equations. So down below, we can see a reaction between carbon, and this is a diagram depicting carbon, and oxygen, So those two are reacting to produce carbon dioxide, which is a gas. All right, so down below, if we were to write this equation, we would start with the reactants on the left. So we would write C for carbon, and it starts out as a solid, so we would write a lowercase s in parentheses. And then it's reacting with oxygen, so we would write a plus sign to separate that first reactant from the second reactant. And then we'd write the symbol for oxygen, which is actually O2. So oxygen gas is usually found in a pair, and we'll talk more about why later. And then we would write a lowercase g in parentheses next to that since it's a gas. And then once those reactants combine, we end up with our product, which will be on the right of this arrow here. And that is CO2, carbon dioxide. And this is also a gas, so we would write a G in parentheses. Now, above the arrow, there's a little delta symbol. And previously, we've used delta to mean change. But in this scenario, it actually means heat. So in order for this reaction to occur, we have to apply some heat. Okay. And then this slide just summarizes what we already went over. So we talked about how we use an arrow to separate reactants from products. And then we separate multiple reactants or multiple products with a plus sign. We can use a delta symbol to indicate that heat is used to start the reaction. And then we also list physical states next to each reactant and each product. So if something is a solid, we put an S in parentheses next to that. Something's a liquid, we put a lowercase l in parentheses. And if something is a gas, we put a lowercase g in parentheses. Now there's one more state that can occur in reactions, and that is the aqueous state, or AQ in parentheses. So this just means that something is dissolved in water, or it's been diluted in water. And this is pretty common in chemistry. So for instance, if you have a solid and you want to mix it with something else, it might be easier to first dissolve that solid in water. Or if you have something that's highly concentrated, but you really don't need a concentrated solution, you can dilute it first. So that would be an aqueous solution. Okay. So now, when we're writing out these chemical equations, we do need to make sure that we have the same number of atoms on the reactant side and on the product side. So this has to do with the law of conservation of mass. And this really just tells us that mass is neither created nor destroyed in a chemical reaction. So another way of saying that is no atoms are lost or gained during a chemical reaction. And this has been proven multiple times by multiple experiments. So the number of atoms on the reactant side has to equal the number of atoms on the product side. So for example, if we start a reaction with 4 hydrogen atoms and 2 oxygen atoms, we have to have that same number of atoms on the right-hand side. So we still need to have 4 hydrogen atoms and 2 oxygen atoms. So that would be called a balanced chemical reaction or a balanced equation. So let's practice balancing a chemical equation. So down below we have a reaction between aluminum, which is a solid, and sulfur, which is a solid. And when we mix them, I think we also need to add heat, so we'll put a little triangle there. We end up with something called aluminum sulfide, which is also a solid. Now, in the product, you'll notice we have a compound. So we have a mixture of two elements. So they exist in a very distinct ratio. We have 2 aluminum atoms for every 3 sulfur atoms. So that's indicated by those subscripts there. Now, when we're balancing chemical equations, what we're going to do is add numbers or coefficients in front of the elements or the compound in order to balance them, but we're never going to change the subscripts. At least not when we're balancing equations. We'll see later on how we determine what those subscripts are. But for now, just don't change those subscripts because that indicates a very specific relationship between the elements in a compound. Okay, so let's balance this equation. I'll show you how to do that. So what I usually do is I write out a little table of reactants versus products. And then I list the elements off to the left. So we have aluminum and sulfur. All right, so then I start counting how many of each element I have on the reactant side and on the product side. So on the reactant side, I have 1 aluminum atom and 1 sulfur atom. And then on the product side, looking at those subscripts, I can tell that I have 2 aluminum atoms and 3 sulfur atoms. Okay, so now I need to balance this equation. So we can see that aluminum is not balanced and sulfur is not balanced. They don't have equal numbers on each side. So let's start with aluminum. We want 2 aluminum atoms on each side. So what I'm going to do is essentially multiply aluminum, oh, not by 3, by 2. I was thinking of sulfur. So I'm going to multiply aluminum by 2. Okay, so I have 2 aluminum atoms now on the left and on the right. So I can also do the same thing with sulfur. I'm going to multiply sulfur by 3 on the left-hand side. So now I have 3 sulfur atoms on each side. So pretty easy so far, right? So these are coefficients. And we would then say that there are 2 aluminum atoms that react with 3 sulfur atoms to give 1 compound of aluminum sulfide, or Al2S3. We'll learn how to name compounds later. All right, so again, remember we never change subscripts. We're only going to add in coefficients to balance these equations. All right, so here are the solution slides if you need those later. So let's practice another equation, and if you want to try this on your own first, you can. Feel free to pause the video, and then we'll go over it together. Okay, so for this reaction, we have Fe3O4, which is a solid, and that's reacting with H2, which is hydrogen gas. And then that's producing pure iron, which is a solid, and H2O, which is water, so that's a liquid. So I'm going to write out my reactants and products table to start. And it looks like we have three different elements here. We have iron, oxygen, and hydrogen. All right, so now I'm going to start counting how many of each element I have on each side. So on the reactant side, I have 3 iron atoms. I have 4 oxygen atoms and 2 hydrogen atoms. And then on the product side, I only have 1 iron atom. I only have 1 oxygen, and I have 2 hydrogens. Okay. So it looks like so far only hydrogen is balanced, and iron and oxygen are not balanced. So let's start by balancing iron. So let me pull up a different color. So we have 3 iron atoms on the left, but only 1 on the right. So let's multiply iron on the product side by 3. Okay, so now we have 3 iron atoms on each side. Perfect. So now let's move on to oxygen. So we have 4 oxygen atoms on the left, but only 1 on the right. So let's multiply H2O on the right by 4. But notice that we're actually multiplying that whole compound by 4. So we're multiplying oxygen by 4, but we're also multiplying the hydrogen atoms by 4 as well. So we're going to multiply 4 times 2. So we're multiplying the coefficient by the subscript, and that gives us a total of 8 hydrogen atoms on the product side. Okay, so now we have a problem. So hydrogen initially was balanced, but now it is no longer balanced. And that happened because we had to balance oxygen. But that's okay, we're just going to go back and balance hydrogen now. Okay, so we want to end up with 8 hydrogen atoms on both sides. So what could we multiply this hydrogen molecule by to get 8 hydrogen atoms? 4. So what we're going to do is just multiply that by 4. And again, we have 4 times 2, and that's equal to 8. Okay, so now our table shows that everything is balanced. But if you want, you can always erase your numbers and then kind of go back through and make sure you have the same number of atoms on each side. Okay, so that means our coefficients are 1, 4, 3, 4. So you could write a number 1 in front of that first reactant, but oftentimes if something is by itself, we just leave it blank. And then here are the solution slides for that problem. All right, so let's do a couple more practice problems. And again, if you want to try these on your own first, feel free, and you can pause the video, and then we'll go over them together. Okay, so let's go over the first one together. And you'll notice that this is multiple choice, so you'll want to make sure your coefficients match one of those options. So I'm just going to make my little reactants and products table, and this time I'm just going to abbreviate it as R and P. And in this reaction, we have Fe2O3 reacting with carbon, and that's producing iron and CO2, carbon dioxide. So it looks like our elements here are iron, oxygen, and carbon. So on the left-hand side, I have 2 iron atoms. On the right-hand side, I only have 1. For oxygen, on the left-hand side, I have 3. On the right-hand side, I only have 2. And then for carbon, on the left-hand side, there's 1. And on the right-hand side, there's 1. Okay, so far only carbon is balanced, but iron and oxygen are not, so they are unbalanced. Okay, so let's start with iron. So if we need 2 irons on both sides, I'm just going to multiply the iron on the product side by 2. Okay, so now that's balanced. Now for oxygen. Oh, this is tricky. I've got 3 on the left and 2 on the right. So I think what I'm going to do, I'm going to multiply oxygen on the left by 2 and oxygen on the right by 3, so that we end up with 6 oxygens on both sides. Okay, so I'm going to multiply this oxygen by 2, so that's 2 times 3 equals 6. And then I'm going to multiply the oxygen on the right by 3. So that's 3 times 2, which is also 6. Okay, so I've got 6 of oxygen on each side. But wait a minute. Remember, when you multiply a compound by a coefficient, you're multiplying all the elements in that compound by the coefficient. So not only did we change the number of oxygens, but we also changed the number of irons. So we have 2 times 2. So now we have 4 iron atoms on the right, or sorry, the left. And then we also changed the number of carbons. So now we have 3 times 1, which is 3 carbons on the product side. Oh boy, okay, so now oxygen is the only thing that is balanced, and now iron and carbon are unbalanced. So this happens. Sometimes you have to go back and forth to kind of figure out the right ratios. Okay, so let's see. So now we actually need 4 irons on both sides. Okay, so what can we do here? So luckily, iron is by itself in the products. So let's just multiply that by 4. So that will balance out iron. Okay, that was easy. But now what about carbon? Okay, so luckily carbon is by itself in the reactants, and we need 3 on both sides. So we can just multiply that by 3, and everything should be balanced. So we have 4 irons on both sides, 6 oxygen atoms on both sides, and 3 carbon atoms on both sides. Awesome. Okay, so that is now a balanced reaction. But additionally, let's check and make sure it matches one of our options here, A, B, or C. So our coefficients are 2, 3, 4, 3, and that matches B. All right, so now let's do the second one. So in this reaction, we have aluminum reacting with FeO, and then that's producing pure iron and Al2O3. Okay, so it looks like our elements are aluminum, iron, and oxygen. So now I'm going to count how many I have on each side. So for aluminum, I have 1 on the reactant side and 2 on the product side. So I got that from the coefficient, or the subscript, excuse me. For iron, I have 1 on each side of the arrow. And oxygen, I have 1 on the reactant side and 3 on the product side. All right, so let's start balancing. So let's start with aluminum. That's not balanced. So we need 2 on each side. So I'm going to multiply aluminum on the reactant side by 2. All right, so that's balanced. Iron is already balanced, so let's move on to oxygen. I need 3 on each side. So on the reactant side, I'm going to multiply that by 3. But again, we're multiplying a compound by 3. So we also have 3 iron atoms now on the reactant side. Okay, so aluminum's balanced, oxygen is balanced, but iron is not balanced. So what I'm going to do, luckily iron is by itself in the products, so I'm just going to multiply that by 3. Okay, so it looks like our coefficients are 2, 3, 3, and 1. And that matches A. Now, again, you could write a 1 in front of Al2O3, or you could just leave it blank. Normally we just leave it blank. All right. And here's the solution slide if you want to practice these later. So on Canvas, there is a worksheet that is all about balancing equations. And there's some easy problems, some medium problems, and some difficult problems. So I encourage you to try that worksheet on your own. I'm also going to post a video that goes over that worksheet. So that will be under week 4 Panopto videos. But I'll try to make it easy to find that video as well. So I'll go over a couple of examples with you from that worksheet if you need some help getting started. But the answer key is also available on Canvas if you want to just try it on your own. And I will see you in the next video. We're going to start talking about types of chemical reactions. I will see you then.